So this is a situation that we have talked about before. When we apply diversity factor, we apply it to similar group of motors or machines. Okay. And likewise, the challenge is for us to be able to find out what is a suitable size for this. And of course, in the process, we need to calculate this. And remember, a good technique that we should always use when we have a three-phase system is to draw a chart like this. Okay, minimally, we should have description of our load. Okay, if you are able to capture the load current, which can be I full load for motors, or it can be I maximum demand for others. In the second column, that will be really helpful. You then have your L1, L2, and L3. To allow you to space out the different load. And of course, as a reminder, your diversity factor. Okay. So in this case, we are trying to fit all these loads into or across the three phases that we have as a supply. Okay. So for three-phase machine, when we see that it is a 100 amp full load, it implies that across all three phases, we will be drawing 100 amp each. Okay. So for three-phase machine, repeat again, when we say 100 amp full load, it means that across all three phase, we expect to see 100 amps. Okay, and if we apply diversity, the first one, the largest one, will be at 100%. Second one at 80, and the third one at 60. Okay. Then we move on to the next category, M2. In this case, the full load is 80, and it is also a three-phase machine. So we put 80 across all three phases. Right? And this is 100, this is 80, and we do not have 60. And we move on to the third category. Okay. And notice that this is a single phase machine. So it means that we have to assign one phase to supply each. Okay. And our aim is to make all the three phases as balanced as possible. Okay. So we can start with 12 here, and we use L2 for the next. Okay. And since we only have two of them, we have nothing here. Okay. Empty. Okay, so far, so this is how we do it. And if, let's say, for whatever reason, we have another M3 that is 12 M one phase, okay, then we will be more than happy to use L3 to supply it. So in this case, we only have two of them, okay, and we notice that there will be some slight imbalance in the system. But it is still okay because the differences is going to be really small. So this is where we will end up. Okay. We will skip this case where we don't allow diversity. We will straight away go to the case where we allow diversity. Okay. So as a reminder again, for three-phase system, we will be using the largest phase for our calculation. And in this case, we notice that out of the three phase, we have two of them which is at 472 as compared to 460. So it will be good if we use either one of them. We will use L2. So maximum demand for L2 here. First term, 100% of the largest motor, so it's 100. Second one, we take 80%, so we multiply by 0.8. So 100. 100, 80, 60. Okay. And then it will be another type of motor. So we start with 100 again. So this is reflected as 100. Next one is 80. Okay. And we realize that in this case, we only have one type. Okay, we only have one of M3. So we will have 12 here, and these two are not required. Okay, and then we move on to calculate IB. Same thing, we only look at phase 2. All we need to do is to replace the 100% full load current of the largest by the circuit breaker rating. Okay. So we only replace one. We do one replacement. Yeah. Notice that we do not replace the, neither do we replace this. Okay, sorry, the marker didn't come out. So I wait for the, okay. So we only do one replacement, and notice that we do not replace the full load current of M2 with the circuit breaker rating. So we do not replace this. We keep this as 80. Neither do we replace this. So we still keep at 12. We only replace the full load current of the largest out of all. There's a question in the chat. One of your classmates asked, okay, in my previous example, what I did was I placed 12 here. Okay. I use L1 instead of L3, but this example uses L2 and L3. Okay. So it doesn't really matter because at the end of the day, you are only going to focus on the largest phase. Okay. So as a designer, you have the choice to choose whether to use L1, L2, L3 for your single phase. The only key thing that we need to do is to make sure that all the three phases are more or less balanced. So we are not allowed or we are not encouraged to put two of the single phase load in one phase only. Okay, the idea is that we need to spread out our single phase load. So whether we spread it across L1, L2, or L3, it doesn't matter. Okay, Ken? And then we will arrive at this 521. And then therefore we select 630. So essentially, I am overlapping topic 5 with topic 3 because topic 5 is going to cover the idea of load balancing. Yeah, which in the process of teaching about protective device for a group of motors, we are also applying it. Okay, so for EID, the concept that we learn are not strictly demarcated by the topic. Whatever we cover in topic 2 can be applied in 3, 4, 5, and so on. Okay? That is why the good foundation is the key to doing well for this module. Okay, so I tend to go slow in the beginning, in the first term, and I will speed up more in the second. Okay, I just want to make sure that everyone gets the basic correct. So we will revisit this idea of load balancing again when the new term starts in late June, early July. And if you may notice that we have introduced, without you knowing, a new protective device. Okay, this is not a typo error. Every one of us is so used to MCB, which is what we call a miniature circuit breaker. Okay, so the word miniature will suggest that there is probably a limit to the amount of current that it can carry and operate. And so, to overcome the current limitation for the MCB, we have a device called MCCB. Okay, we add another C to it. And this is what we call the molded case circuit breaker.